All right, I'm connected. So let's hope that this records. So got a worksheet, 53 questions. I think this will be part one. I'll do the first 26 or so. And it's, I think, designed for students who have finished Algebra 1, who are moving at a quick pace and have had a few discussions about geometry of change and derivatives. And certainly can do that at the Algebra 1 level. And I think it should be done because you don't want to wait to hand difficult concepts to students in one course, usually at the senior level at high school. It's just not enough time to process integration and differentiation. So I think a lot of seeds need to be planted at an earlier age level. And I think we can do that and to some extent at the elementary school level as well. I've got the worksheet on the board. I'll bring the computer over in a second. You can screenshot if you decide you want to try to answer these questions along with me. Again, I don't expect to teach these concepts on the spot, but I certainly think they need to be introduced so that the neurons can begin to connect. Problem one on the test, on the worksheet, it's a group project. I usually do it about 4 weeks into a calculus course. Because by then we've covered all of the topics that are on the worksheet, and it's a chance to connect them to a physical situation. Not a physics teacher, so hopefully some of the terminology I use is not wrong, but the symbolic rulers video would be helpful if you saw that prior to doing this. Not necessary though, because I'm going to get us started with the first question. And the relationship between differentiation and integration, and put those notes on the board to remind me to say them, I think would be a very useful video to look at before you tackle a calculus class. I've used Desmos to help me sketch a variety of functions here. And the old rotator cuff surgeries, you can see it's a little shaky on the curves that I tried to, trace. All right, let's have at it. Let me show you the worksheet, and then I'll have to take the worksheet down because I haven't written the problems out. Let's see if I can capture the worksheet on the wall here. And then I won't move anything. And I guess if you screenshot that and make it bigger, you'll see what questions I'm going to ask. And then part two, let's see if I can get that to hold here. Come on, there we go. Part two, there's part two, screenshot that. And, I hope that's sufficient way to get you to see what I'm going to be asking. All right, so let me move my trusty cart into a better position. Let's see if that captures everything. Yeah, I guess that'll do for now. All right, so the first question is, Mr. V, I guess that's me. Kicks the ball straight up into the air and leaves his foot from a height of 3 feet. So the ball's here, striking it straight up. Nice, no knuckle. Come down to the top of the foot, repeating it 10 minutes every day, alternating feet. Just giving you some tips as to how you can improve your soccer game. And so we're going to write a function that relates the height of the ball to time. All right, from the Algebra 1 class, we've got 2 points. We've got the vertex. We've got the initial starting position. So the vertex, t minus 2 squared plus 67. What have we gone? 67 to 3. We've gone down 64 feet, and it's taken a quadratic change of 4. Okay, so dropping in a 0 and doing the conversion is what the symbolic ruler is about. And so that's h of t. All right, we already got our roots when it hits the ground, right? This is minus 16. That's your a term. You've got a 267, so your algebra 1, I hope that, 67, you got to drop 67 feet. You got to divide by minus 16, 2 plus or minus. Okay, there's your roots. Just thought I'd show you that. We've been working on that in algebra 1. And if you write that as a decimal, it's about 4.046 seconds. It hits a height of 0. All right, so what is it in terms of AT squared plus BT plus C? If we rewrite that, then h of t is minus 16 t squared. Can that be seen? Maybe I got to go back a little bit more with this card. You can tell that this is not a professional. Videoization, is there such a name as that? Who knows? So h of t minus 16 t squared plus 64 t plus 3. All right. So that is our height function. Maybe I can write it up here. Maybe I'll put h of t equals minus 16 t squared plus 64 t plus 3. All right, that's the concave down graph. All right, what questions have I asked? All right, so that takes us through problem 1 and 2. What is v of t? Well, if you've looked at the geometry of change, then we're only dealing with a quadratic. Yep, you can see this. And I put a couple of changes here from 2 to 2.01, 001. We get 4.004001. And that is discussion is had in the relationship between differentiation and integration. I kind of spent a little more time on the geometry of change in that video. Certainly spent a lot of time geometry of change on a qubit. So 3.001 gets us 9.006.001. And 4 I decided to do some more decimals. 1, 2, 3, 4, 5 gets us 1, 2, 3. I think I missed a 1, 2, 3, 4, 5. So there should be another 0 in here. 1, 2, 3, 4. That's better. And there should be 1, 2, 3, 4, 5 at the end. And we can start to see the change at 2 in a quadratic. The change at 2 is going up at 4 to 1. And then it's going up at 6 to 1. And then it's going up at, so we get the, the changes by a layering of drawing 2 more sides. So integration, adding up all of those little changes, integration takes us from a smaller square to a bigger one. And it's really the derivative of x squared is, y prime, we'll call it 2x, all right? Twice the size of the length of the sides of the square. All right. So what is the derivative? Again, we've already been doing some calculus for a while. So what is the derivative back this way? Oh boy, this is kind of a shaky video. All right, but it's planting some seeds. So we know t squared is 2t for a change. And if you multiply by negative 16, you get minus 32t plus 64. All right, rates of change, composites. Let's say you're a babysitter and you get paid, P of X, paid $5 an hour. Okay, but then the raise, call it R of X. When you get good at it, you get doubling the number of hours you put in. I don't even know if I wanted to say it that way, but you're doubling 5H as a function, and pretty quickly you can see you got $10 an hour. Right, so we've got a little bit of multiplication taking place here. So you can think of 2t as the derivative of t squared, and you're multiplying it by negative 16, brings in the rate for this term. 64t, what's the rate of a linear function? Well, every second, time is in seconds here, right? So 2 seconds to come up. So every second, you're going 64 feet per second. Well, you've traveled 64 feet. So that's the rate, right? That's a constant, right? It's a constant rate, linear function, changes to that constant rate. And the number 3 is a constant. And so if you see that number change, please call your health professional immediately. Okay? I don't think that's changing. Okay, so constants don't change. So the derivative has a plus 0 there. All right. So we've got our first derivative. What's the second derivative? Well, the second derivative is the rate of change of velocity is dictated by acceleration. I used to call the pedal on a car the accelerator. I guess the brake is the decelerator. All right, and so it's a constant, right? It's a linear function. So the acceleration is minus 32 feet per second squared. You're going to get a y1, y2 minus y1 over x2 minus x1 thought process. And so, this is change in seconds, and we've already got change in seconds. So change in seconds squared. I don't want to see a second squared running around campus. I think it would scare me. All right, so Desmos. I put these on Desmos using the domain and range stipulated. All right, so we're talking about acceleration, minus 32 acceleration. What does that tell us about velocity? Well, let's look at velocity. Velocity is always decreasing. So it looks like our acceleration should be negative, right? And how is it decreasing? Well, it went from velocity was initially, I guess at 0, velocity was minus 32 times 0 plus 64. I guess that foot put 64, a force of 64 feet per second on that ball. It's going into space right now. I can see it. Past the moon? No, it didn't take, it takes a lot longer than that at 64 feet per second to get past the moon. But it's going up there. I don't think it escaped the Earth's atmosphere yet. No. Anyway, velocity is decreasing for some reason. That ball just doesn't keep going up. Can't imagine what the reason is. But it's got an initial 64 feet per second going up, and it starts at a height of 3. I guess a tangent might be helpful here. So the tangent at that instant is 64 feet per second, and we're starting at a, that's the tangent. Geez, wow. Well, anyway, just trying to look at this with a critical eye. I noticed that matches up with that. Oh, okay. It's probably a coincidence. A appears to be less than 0. What does that tell you about h of t? Well, h of t is a concave down shape, right? So if we kept drawing tangents, there appears to be a very important one here. A tangent has a slope of 0. That's good. And then the tangents. Yeah. It sure looks like sure looks like those velocities are decreasing. Yeah, I think this has something to do with if the acceleration is negative, then we're on a concave down interval. Does seem to suggest that. We'll talk about that more as the term goes on. B of t appears to be decreasing. What does that tell you about h of t? Well, if velocity is decreasing, I actually do my calculus course based on traveling on Route 91, a north-south highway near here. And we talk about, above the border between Vermont and Mass being positive mile markers and below negative. I got a feeling that if your velocity is positive, velocity is positive from 0 to 2, then the height of something is going up. And I guess if the velocity is negative from 2 to 4.046 before the ball hits the ground, it sure looks like velocity is negative, and it appears to be creating this concave down shape. Okay. I wonder what's causing that. Oh, well, let's continue on. What is the velocity of the ball when it hits the ground? Well, I think I allowed students a calculator for that, and we got to find out when it hits the ground. And I think we did that already, didn't we, at the beginning of the video? We've got the 267. Oh, yeah, we went down 67. Yeah, we already did that. So we put that in the calculator, and we found it's 4.046. And I wanted to get a quick feel for that. And I didn't have a calculator with me. I had Desmos, which is, I suppose, a calculator, but I didn't know how to use it well enough. So I just looked at, we changed 3 feet in 0.046. That gives me the speed at which I'm hitting, or the ball's hitting the foot. No, the ground in this case. I missed it. God, should have practiced more. And I think it came out to be, 65 point something. Right? And geez, that's pretty close to this 64 number. But it's just a little bit more. Maybe because it kept falling a little bit longer. And I don't think I'd want to hit the ground traveling at that speed. Yeah. But the velocity is the negative of this, right? Because you're going down. But speed is the absolute value of velocity. So that would tell you something about the rate at which it's hitting the ground. Okay, the speed at which it's hitting the ground. Well, going through this video a lot faster than I thought. Maybe I could do the whole thing in one. But maybe should replay this because I have no idea how this is being viewed by you. So let's see. Estimate, where am I? Estimate the area of the velocity curve from 0 to 2 using 4 left-hand Riemann sums. Okay, Riemann, good man. Got us rectangles. So I'm doing 4 Riemann sums under, what did I say? Velocity curve. All right, so I'll do a dotted line. So here's the velocity curve from 0 to 2. And I'm going to do 4 rectangles. So the second rectangle should be, I guess, halfway. Yep. And then there's halfway. And then there's halfway. That's the best I can do. Left hand. This is the left side of the rectangle I'm going to draw. And I'm going to do a dotted line. The left hand from here. And not too bad. The left hand from here. And the left hand from here. And I think you should watch a video like this just casually and then come back to it and see it again. And if you do it 4 days in a row, you probably own all of these things. All right. Now I got to estimate the area under the velocity, but I can use a calculator, so I'm not going to actually do it. But I do know the height of this one. The height of this one is 67, right? Okay. No, 64, excuse me. 64, right? And then I mean, I could plug in 1 here easy enough and at least get this one. So let's see. So that's 32, right? And that's going to be for a half a second. And then this one is for a half a second. And then if we put in 1/2, well, that's not too bad. Here, I got these nicely. So half of this is -6, that's 48. I should have known that. I've had my coffee today, but I'm getting old. And then if we put in 1/2, 3/2, we've got I guess 16, huh? Let's see. We got 64, 48, 32. Nice little pattern here, right? So yeah, so it looks like that's going to be 16. And so it looks like I've got 1/2, and I'm doing it to 64. That's going to be this area. And then I'm doing it with 48. Then I'm doing it with 32 and 16. Okay. And so, you know, why don't we just cut these numbers in half and then add them? It'd be easier. 32, 16, oh God, 24, excuse me. 24, 16, and 8. 24 and 24, 48, and 30 is 78, 80. Okay, so according to Riemann, the approximation is 80 feet, right? Because if you're multiplying seconds, let's do that, times feet per seconds, right? Then we've got seconds times feet per second. That's telling us how far the ball has gone if it was from 0 to 1/2 second at a constant rate. Okay, but we've got a decreasing rate. All right. So now the next question is, I'll erase that. Is your answer an underestimate or an overestimate of the actual area? Well, I think we got error here. Right? So it's an overestimate. Because we've got a concave down shape, by the way. That's another reason. Find the value geometrically. Well, let's look at the geometry of this. It does seem to give me a shape. Yeah, I'd say that's a triangle. I would say that's a triangle. And so if we have a height of 64, and we look at the width, which is 2, and we cut that in half, I do believe the actual area under this curve is 64. So the ball has kind of changed position from 3 to 67, and it appears to have changed by 64 there as well. Must be a coincidence. Okay. Find the value using the fundamental theorem. Well, the fundamental theorem is integrating from 0 to 2 with the velocity, minus 32 feet per second, and initial velocity of 64. Put that in parentheses, dt, and using, you know, the inverse of differentiation. So going up 1 and dividing gets me minus 16t squared plus 64t from 0 to 2. I think we can see when we put 0 in, we're getting 0. So let's just drop a 2 in. 4 times minus 16 is negative 64. And putting in 2 here is 128. And I guess 64 from 128 is 64. So the first fundamental theorem tells me that the ball's traveled 64 feet. Must be a coincidence. All right. What was the initial velocity of the ball? I think we did that earlier in the video. Well, it's not the first time you've heard it, but let's drop 0 in to the first derivative here. Negative 32 times 0 plus 64 means that, yes, we're going up at 64 to 1 at that instant. So we can do that. Write the equation line tangent to h of t. Geez, I already did that earlier. Notice anything? Yeah, I did. I hope you did too. That the equation of the tangent to this polynomial. Oh, I wonder if that happens with all polynomials. I wonder if we can think about an initial value on the y-axis and how it's changing at that instant. Probably a coincidence. Okay. Okay, so we already wrote the equation to the tangent. 64t plus 3. All right, find the maximum height of the ball by using calculus. Well, we know the maximum height is 67. But what happens with the velocity? Well, the velocity changes from positive. I mean, it's slowing down, but it's still a positive velocity here. As we can see, the slope of the tangent is increasing. But it equals 0 here. And then the slopes of the tangents are negative. Well, I think positive slopes are slopes that go up. Negative slopes are slopes that come down. I got a feeling we're getting a maximum right there using the first derivative test. Because it equals 0 and changes signs. The first derivative changes signs and the function equals, and those velocities equals 0 there. Which means we have an object at instantaneous rest. Tell me how else I should describe that, and I will. And before that, it's going up and then coming down. So that's the first derivative test. Now, where am I now? Second derivative test. Well, what did we say happens with the second derivative? It's always negative, which means we have a concave down shape. We can see the concave down shape with a tangent whose slope is 0. Again, I think that's giving us a local max. In this case, it is the max of this function. But we could find all kinds of local maxes and local mins if we know the slope is 0 here and 0 here, right? So slopes are going down, negative, then they're going up, gives us a minimum. Slopes positive to negative with the 0 give us max. If we can prove concave up, we're producing, that's a second derivative test. Concave down, right? Second derivative test distinguishes between local maxes and local mins. Right, you hear that 4 days in a row, you might own it. What was the velocity of the ball after 3 seconds? Well, we got a function for that. Drop in a 3. Minus 96 plus 64. I guess that's probably minus 48. Because the acceleration is gonna, well, I think a ball falls 16 feet in the first second. Not doing this in meters. I'm old-fashioned here. Where are we at? What was the speed of the ball at that instant? We already talked about that. Speed is the absolute value of velocity. All right, so we drop in 3, even though we get minus. So at 3 seconds, right? The velocity at 3 seconds is probably right there. Is minus 48 feet per second. And the absolute value of that means that it's moving at 48 feet per second. If grandma was on Route 91, it means she's headed south at 48 miles per hour. Yeah, I guess I don't have to go out and get her. A minimum speed on 91 is 45. So she's in the way of a lot of people, but probably safe enough not to get hurt. Okay, but that's why we study calculus, to rescue grandma off of Route 91. All right, justify your answer. I don't have to justify going out to help grandma. All right, 25. 0 to t. We got to do this calculation. 0 to t minus 32a. Those are called dummy variables in calculus because they're going to disappear. Plus 64 dA. I could have called that any letter because we're going to drop in t and 0. And when we do that, we're going to see this turn into a function of time. All right, so 0 gets me, where am I? Oh, yes. So again, the differentiation, right? I'm going to add 1 and divide by that number. Minus 16a squared. plus 64a from 0 to t. Okay? And I think I probably can erase all of this now because we're done with the first side of the sheet. Okay, so I'm going to erase over here so that I can do this out. Do the fundamental theorem. Okay, so we're going to drop a t in, and that's going to get us, I'll put it in parentheses, minus 16t squared plus 64t minus, what I'm basically doing is from a to b fx dx, the first fundamental theorem, some people call it a second, f of x, f of b minus f of a, right? And big F, little f is another notation system for, that's our height function, that's our velocity function. Okay. So I'm dropping in 0 now, and I'm going to get 0 plus 0 here. And so what I have is, did I forget to write +3 here? I bet I did. I did, right? So on the sheet, there was also a +3 here. So we have to put a +3 here as well. And so the integration from 0, and that number actually gives me h of t equals minus 16t squared plus 64t plus 3. So, wow. Wow, this 0, and that 3. Okay. Must be a coincidence. Must be a coincidence. So let's try another one. So the next one is 1 to t. 1 to t. All right, I should change this up and do 2 to 67. It'll be easier for you to follow. So let's go from 2 to t, and let's do the same thing. Minus 32, let's, instead of a, let's use m, let's get daring. Plus 64, all right, that's the velocity that we're looking at. Let's use dm, and let's erase the fundamental theorem and see if you can remember it. Let's do this one on, oh, wait a minute, plus 67. Yeah, I think I'm using an initial condition and velocity. So initial position and a rate. Let's see what we get when we do this. Again, minus 32 m squared divided by 2 gets me minus 16 m squared plus 64 m from 2 to t. In this case, I didn't forget to write plus 67. Let's go here. We're done with this for now. So we drop a t in, we get minus 16t squared plus 64t minus, we drop a 2 in. Ooh, I got to do some math. I got to get rid of the layering process of differentiation. Okay, and I got to add 67 here when we're done. And so we drop a 2 in, and we get 4 times minus 16 is minus 64. Wait a minute. I forgot what I was doing. Started in here. Okay, so I drop a t in, I get minus 16t squared. Now, I was right, I knew what I was doing. 64t minus plus 67, my fault. Drop a 2 in, you get minus 64, I think I just said. Plus 128. Okay, so that's minus 16t squared plus 64t. My brain was getting slow. Often happens to be minus, adding that is, where did I go wrong? Oh, right here, my fault. So I put t in there, squared. 2, oh, doing a minus. Geez, okay, brain stop. I'm not gonna do the video again. Getting old. And so therefore I've got h of t equals minus 16t squared. I should have been doing this without the glasses. Plus 64t plus 3. Wait a minute, that's the same thing we had before when we did from 0 to 3. I wonder if the accumulation of area under the velocity curve from 0 to 2. That seems to be a constant area. So depending upon where I start to do the derivative process, the accumulation, I guess this has something to do with where I am in a table of values. All right, I'm getting real tired here. So I'm just going to be quiet, stop this video, and hope that some of that plants a seed. Oops.